Thank you, thank you. So this is a rectification tower. These rectification towers, they are used in oil refineries to separate fractions of a crude oil into these fractions like petroleum, kerosene, asphalt. And for the process of distillation, which happens in that column, it is crucial to maintain the correct temperature of the crude oil that boils. As software engineers, we are probably, like most of us, are coffee lovers. So we all know that for coffee brewing, temperature stability and having correct temperature of water, of the brewing water, is really critical for the taste of coffee, right? If we will have too low temperature, your coffee will be sour. With too high temperature, it will be over-extracted and bitter. So here, the temperature control is also really critical. And this is a handle that allows us to control the so-called cruise control system in car. That system allows you to set up the speed of a car while driving on a highway, and the car will maintain the speed for us, and our right foot can rest, and you can basically like let the car to maintain the speed for you. And these images here are not by accident, because they all share the same property. They all use so-called PID controller to make them working. And today I'm going to show you that Redpanda is also using PID controller in the background to control the priorities of so-called backlog tasks. And as you already know, my name is Michał Maślanka, and I am a software engineer in Redpanda. On the daily basis, I sit in the basement and write C++, mostly in the area of Raft and the parts that orchestrate single nodes to form a cluster of Redpanda. And this talk will be split in 3 parts. In the first parts, I will go over the Redpanda internals and what is the backlog task and how C-star cooperates with Redpanda to prioritize those tasks. In the second part, I would like to show you the PID controller, a short introduction, and we'll try to have an intuition of how does it work and what is that. And in the last part, we'll deep dive into the implementation details. I will show you parts of code, and also hopefully we'll see it in action during the demo. So let's jump right in. The motive of this presentation will be Redpandas, obviously. So we saw from colon feeds. I will have pandas, so they will appear from time to time. So Redpanda is a Kafka-compatible streaming data platform that is built on top of C-star framework. And C-star is an asynchronous C++ framework designed to build data-intensive applications. C-star leverages this thread per core architecture, where each thread is pinned to CPU core, and that's named a shard in C-star lingo. Shards here on this picture, they are like marked with different colors. And each shard, they do not share any memory. So we name it a shared nothing architecture, and developers are forced to exchange messages between, exchange information between application threads in form of message passing. So there is no shared memory between shards. And C-star also implements so-called user space scheduler that leverages the cooperative multitasking pattern. And in Redpanda, we use C-star fragmented buffers, shard local memory buffer pools, and direct I/O directly bypassing kernel page cache to leverage to provide the best possible performance out of your hardware and scale with the hardware. As we know, like currently machines we operate right now are far different from what we saw like even a few years ago. Now, as we sit here, probably most of you are familiar with Kafka data model, but I will briefly go over that as Redpanda uses the same abstraction layers. So in Redpanda, data are organized in topics, and topic may be seen as a set of partitions sharing the same configuration. And each partition in a topic is really an immutable append on the log that in Redpanda is backed by the Raft protocol instance. And that's what differentiates us from Kafka at this point, as Kafka uses so-called in-sync replicas as a replication protocol. So as we said, we have partitions, immutable append-only logs, and each single message called a record in Kafka lingo is really a key value tuple. So this is how Kafka represents data. So a key value and a header, and these data are organized in the partitions in such a way that they are basically layered in the log and indexed with this monotonically increasing number, which is called offset, and each offset is uniquely identifying each record. And while they are sent in the Kafka protocol, they are gathered in so-called batches. So we have records and record batches at the Kafka protocol layer. And now, as we said, the immutable append-only log, right? But it wouldn't make sense if we will only allow user to write data, as that would lead us to a situation in which the disk would be quickly filled up and the Redpanda would stop accepting writes, basically. So it wouldn't crash, but stop accepting write, but it would make application unavailable. So Kafka and Redpanda provides two cleanup policies, so-called. And first of them is this deletion cleanup policy, where a user can specify data retention in terms of time, which is the time that we want retained data. It's like saying, I want my data to be not older than a week, or a size, like I want at most 1 gigabyte of data per partition. And what deletion does, it simply deletes data that are older than a certain threshold. So it deletes the oldest records in the log and only preserves the most recent one. And the second cleanup policy is so-called compaction. And compaction leverages these key value tuples. And it works like that only the most recent value for a given key is left after the compaction process. So as you can see, like for example, for key 1, that would be the value at offset 3 will be discarded, and only the value at offset 9 will be actually promoted and stored after compaction. So this can be imagined as a process of building simple map in our application, and whenever a new value for a key appears, you simply replace a value in a map. So this is roughly what compaction does. And compaction is a IO-intensive process, as this data has to be read, right? Even if we will have an index, they have to be read, and then they have to be deduplicated, and then stored back again. So we see that it's both IO-intensive and CPU-intensive process. And what is also important to be observed here, this compaction grows, the amount of data to be compacted grows with the time. So as we write data to Redpanda, the amount of data to be compacted is bigger and bigger. And this property is the same for the process of archiving data in a service that we provide, which is called tiered storage. And tiered storage is a service that allows you to basically extend your retention period. Like we always operate in clouds with NVMe drives, local drives that are local to the VMs, and they are expensive, and they are limited in size. And very often customers look for cost reduction opportunities. So we provide this service tiered storage which allows Redpanda, before deleting data locally from the local disk, we upload them to object store, like S3 bucket or Google Cloud Store. And then this data, they are still readable through Kafka protocol. Obviously, user has to accept the latency, as this data may have to be downloaded before to the cache, and only then can be delivered to the consumers. So this operation, like uploading data to object store, it has the same property as compaction, right? So as we write data to log, the amount of data to be uploaded to object store grows. And so this is this interesting property, and we call it a backlog growing task. So as the time goes, the backlog grows. And both of these tasks, they have this, they are background tasks. They are not important enough to influence so as we say about that the hot path. So they do not directly influence write latency, read latency, but they may indirectly influence that, as this process will consume I/O resources and CPU resources, CPU time. So we need to somehow control the amount of resources that we give for these processes. And the way we do that is by leveraging C*, and C* gives us two perfect knobs to do this. And one of them is an I/O scheduler. So C* has user space I/O scheduler, and this diagram here, on the left-hand side, we can see different classes of requests, of I/O requests, like compaction that I mentioned. Requests, those will be requests coming from Kafka API, so that will be our hot path, our critical workload, as this is what users care about, latencies and throughput of this. And then the recovery, that will be the traffic related with moving partitions around. So whenever we want to spawn a new partition somewhere, we need to populate it with data, and that will be this recovery traffic. And I/O scheduler allows us to assign each of these classes of requests to different priority queues, so-called, and set a separate priority for that request. And also it has, and then it dispatches this I/O according to that priority, so that they are, so the resources are shared according to the priority. And there is also another important job of the scheduler, as it executes as much as it can, but no more than this. So the C* scheduler is clever, and it keeps this latency of this last arrow here. The latency is predictable and small, and it propagates back pressure from disk to application layer, so that it's application developer responsibility to maintain these queues small and with predictable size. Otherwise, the latency would propagate farther to the clients. And another knob that we have is a CPU scheduler. So CPU scheduler, as we already said, it's a cooperative multitasking scheduler, and each of these tasks, as you can see, those are these color-coded boxes. They are atomic, and they explicitly yield control to the scheduler. And here is the concept of the task queue, where CPU scheduler dispatches tasks based on the priority of a task queue, and basically distributes the available CPU time to the task according to priorities. So we see that we have these tunables like CPU shares and I/O shares. And these tunables allows us to control the execution of the backlog task, as we saw. So how would you set up the scheduler in this case? Well, I think that the abstract way to set up it is pretty simple, right? It should be enough, but no more than enough. So it should be as least as possible for the backlog not to grow indefinitely, and keep it stable. But yeah, it's like, so we don't want to put that burden on our clients and on our support team, on ourselves, so that we would have to, every time we deploy a new Redpanda instance, we would have to go and tune that according to the workload. And also workload can change, as Andy said during the first lecture, right? With the time, the workload will evolve. There is probably no good copy of that data. There is no staging database, no staging cluster that executes the same. So it would be, in general, hard. And this is where these PID controllers enter the picture. So PID controller is a device designed to control processes in this closed loop environment, so-called control with feedback. And I will use here an espresso machine, as I am a coffee lover, as an example, so that we can have an intuition of how the PID controller works and what is that actually. So the closed loop control system works in a way where you have a set point, like imagine I want to brew my coffee at 95 centigrades, and we have a way of measuring an output of the process. So in this case, that will be measuring a temperature of a brewing water. And then this is simply subtracted, and the difference between the two values, so the set point and the output, is processed by the controller, and it generates a signal that then influences somehow the output value. So in the case of espresso machine, that will be simply like a, I don't know, duty cycle of a heating element, or basically a current that flows through the heating element that heats up the water, and by that controls the temperature. And PID controller is basically this function. So it's a function of an error. So this is this E value here. And I will just briefly go over that. It has this proportional, integral, and derivative part. Oh, sorry. Where basically a coefficients are multiplied by either simply an error function or an integral of an error function or a derivative of an error function. But let's put this math aside, because that may be complicated and seems complicated at the first sight. But let's try to have this intuition of how does it actually work, and why are there these components of the PID controller. So the proportional part, that's the base one. That's something which tells us how we would translate, say, a 1 centigrade difference of a temperature on the input, like in case of an espresso machine, to actual output in, say, like a duty cycle of an espresso machine heating element, right? So how would this 1 centigrade translate to a percentage of a heating element power? So that's easy. And then we have this tool, the derivative part. So the derivative in the mathematics is basically a rate of change, right? It expresses a rate of change. So the fastest the thing happens, the fastest the thing changes, the larger the derivative will be. And so in PID controller, the derivative part is there to quickly act against the changes that happens quickly. So imagine a situation that we like flush our espresso machine with fresh water, like cold water. And the integral part, this is probably the most complicated one to explain, and it's like the least intuitive one, but basically it's there as for the system to generate any output, the error has to be larger than 0, right? So if you would have a situation in which there will be like, I don't know, a wind blowing on the espresso machine, it will constantly call it out. And then there will be always some difference between the set point and the output value that would generate enough power that this proportional part would, in this steady state, make it all constant. And this integral part is there, it just sums up these error values over time, and it will make this control signal larger and larger. And it will become large enough to minimize that error and actually move our output value to the set point. So it's really important for these PID controllers to set the coefficients correctly. As you can see here, I made a simulation of 3 the same closed loop control systems with different parameters. As you can see, like probably what we want is the blue line, where there is like a slightly overshoot and then the value is constant. But you can see that with different parameters we can have oscillations like the green line, or even like the system may become unstable like with the orange one. So obviously Redpanda has to use a digital version of a PID controller, as we are the digital system and we do not have like functions and continuous signals. So we are using this where integrals are replaced by sums and derivatives is replaced by simple difference of samples. And now let's deep dive into the implementation of Redpanda backlog controller and how it all looks from the code perspective. So I will be showing a little bit of a C++ code. And this is how we build our Redpanda controller. So it accepts this sampler, which is basically a callback that we will call every time the output value has to be measured, a logger reference, that's for the logging purposes, as this class is generic. So we want to differentiate somehow in logs from which class the log is coming out, and then the configuration. The sampler, as we said, it's a function. As you can see there, it returns a future, and that's the way how we express asynchronous operations in C star. So basically, this will be like a scheduling point, so this code inside this function, when it's waiting for that future result to be present, it will yield to the scheduler. And then we have the configuration where all the coefficients are, and also that you can see that there are two variables coming from the SS namespace. That's a shortcut from C star, and those are the primitives that allows us to control the priorities actually. And how it all works, so we basically schedule that in constant intervals. We arm the sampling timer, take the sample of a backlog at some point, and then we use normalization as we want this, the whole setup to be movable from one point to another. And imagine a situation in which you have a machine with like 2 terabytes of disk, or a machine with 10 gigabytes of disk. So for those two machines, the backlog size that is critical will be like totally different. This is why we need this normalization, so that it's like more generic. And here we calculate the parts of a PID controller, so like integral coefficient, about the integral, the derivative coefficient times the difference, then the proportional part. Then we clamp it, obviously, because we need to be in certain boundaries of the shares. Like we don't want this backlog task to have never like 0 priority. We always want it to be in some kind of boundaries. And then we simply call set, right? This call await it's a way to say that this set returns also a future. So that's a scheduling point again, and this is C++ coroutines. And now I would like to explain you, so we saw a generic implementation of PID controller in Redpanda, and now we'll go into the details of how we calculate the backlog for compaction, as I find it pretty interesting. But for that, I need to make you familiar with the directory tree that we are using and how we are actually store data in Redpanda. So the first level here is a namespace. Then we have a topic, so we have a namespace Kafka, topic test, and then we have a partition number, and there is also a number after underscore. That's a so-called revision ID. It's not that important, but we use it to differentiate between two instances of the same topic partition. So like you can delete the same topic and then create it once again. That has to be different topic, right? Because that's the topic coming from the different epoch. So that's this epoch here. But basically what is most important for us here are the log files. So the log files are where the data are actually stored. They are the files that are roughly with the same size. And besides the log files, we store indexes as well. And now let's try to think a little bit about how we calculate the size of a backlog. So as we said, we need to be able to calculate that size at every single point of time, right? So I want to say, I want this backlog size right now. And it has to be pretty accurate to actually, because that's what we measure. So the things are pretty simple for simple single segment, as the compaction works like that before the compaction segment has size A, and then after the compaction, it will have size like this, right? So we have S1 prime, which will be the compaction factor times S1. So we know that data after compaction should be smaller, right? The segment should be smaller, so this compaction factor is a ratio of a size after segment is compacted to the size before the compaction. And we track this compaction factor as a exponential moving average. So basically, we assume that the data in the partition, they are heterogeneous. So we track this compaction factor, and then it's simple for a single level where segments are self-compacted, like the the bottom line here. But then there comes so-called adjacent segment compactions. So we have segment 1 and 2 compacted together into segment 4, and then the result is compacted with segment 3. So then we will end up with like this more and more complicated equation, and eventually it boils down to these two sums. So basically, this is how we calculate this compaction at every point of time. So now I will just show you the code, as there is like another interesting part. In Redpanda, we have right now this limitation that we try to alleviate, that we store data in the same, we only allow to store data from the same term. Term, I mean raft, leader, epoch, in the same segment. So we need to gather segments coming from the same term and only do self-compaction and adjacent segment compaction within the term itself. So this is how we collect that, right? So we check the term of the segment. You can see this like on line 17. Then we collect them in this map, basically segments per term. Then we take this compaction ratio, and that's the exponential moving average from all the previous compaction that happened. And this is where we have these two loops, right? So they are reflecting the two sums. There is also another loop on line 25, which actually iterates over each term that we gathered. And how we actually use it in practice? So in practice, as I said already, we normalize it with the disk capacity. So we have a backlog, which will always be from 0 to 1,000 basically. And we want our backlog size, that's our set point, to be 10% of a disk size, basically. Like that's what we do in Redpanda, and this is what the settings that we use. So we create this configuration object, again, on line 31 and 32. That's probably the most interesting. Those are the primitives that we pass in to control the priorities. So right before the demo, I would like to share with you like the key takeaways that I see from this talk. So I see Redpanda as a modern data streaming platform that is Kafka compatible, and Redpanda is built with this philosophy to scale with modern hardware. The PID controller may be helpful for you whenever you will stand against the problem that has measurable output, and you need these self-adaptive capabilities. And last but not least is to think outside the box. We already had during this conference a talk on genetic algorithms, right? So this is an inspiration that came from nature. Here we have an inspiration that came from industry. So it's sometimes good to think outside of the box, outside of the computer science boundaries. And now let's take a look at the demo. Yeah, hopefully you are not looking like this panda after that talk. So I have a demo here, and basically what I will like to show you, it's this screen, sorry. I cannot click this. Let's do it like this. Okay, so I have here single instance Redpanda running, and this demo is pretty synthetic, as I didn't want to. It's very hard to predict the behavior of a system at saturation, especially in the environment like this, where I'm in the conference, and I didn't want to stress myself. So I prepared pretty synthetic example where I tuned this Redpanda to actually show what I want, but it's actual Redpanda without changing code at all, but I just slightly tuned this PID controller parameter to better reflect what I want to show. So here I will. So you can see here Grafana, right? Maybe I will make it larger so it's easier to see. And what I want to show you is, I know we are running out of time, so let's just do it real quick. So I'm going to start a producer right now, and this graph should be refreshed every 5 seconds. So I started a producer that creates a topic with 16 partitions. Basically, we create first topic with 16 partitions. This Redpanda has 4 shards, and so 4 shards, that means it uses 4 cores. And right now you will see how this is all work. So we already see that these metrics, they are showing us what is happening here. Right, so here on the top, we see normalized backlog size. That's the one that I told you about. So we sample the backlog, calculate these 2 sums. Then we have bytes written to disk. So this is roughly how fast we write. Obviously latency, compaction factor at the top, that's the exponential moving average. So this is how we calculate compaction factor. And the way I use this producer is basically I have a key set cardinality property on the producer. So every time I need a key, I just randomly choose a number from like a range of from 0 to, in this case, 30,000. So there's 30,000 unique keys. So every time we compact, we should left with 30,000 elements in the segment. So yeah, let's just wait for a while so that it will populate itself with the data and actually have something to do. So you can see the backlog is growing as we are writing to the compacted topics. The bytes written to disk. This is roughly what I expected as I set it to 50 megabytes per second. And number of active log segments is growing here. You can see number of size of partition is growing. So this is all expected, right? And let's wait for just a second. So it all has its own inertia, as it has to populate, and it has to write enough data for the compaction to actually kick in and for this controller to work. And here it's the priority. So on this yellow line here, that's the output of the controller. So we should be seeing it changing. So I set backlog to 100, just so to say you what is the backlog here. We can see it's like roughly 60 right now. So in a second we should be seeing it PID controller kicking in. I feel like I should tell a joke right now or something like this as we are all waiting. I have log in here on my screen, and I'm just taking a look at what is the oh, you can see it right now. It starts kicking in as we are already at 100 there, right? So here we can see that the shares are increasing, so that it's like start prioritizing compaction as it grows large enough, that the backlog grows large enough that it's over the set point. So now what we should see, like we'll probably not have time to see it, but basically the idea here is that this value will be constant at some point. It will reach some point and then it will be constant. And this way, that's the enough, but not too much value that we want to see. Yeah, I think that's it. So if you have any questions, I will leave some time for the questions. Thank you very much for your attention.